In this problem, I receive an array of integers and need to determine the pivot index of this array. The pivot index is the index where the sum of all numbers strictly to the left of the index is equal to the sum of all numbers strictly to the right of the index. If no such index exists, I should return -1. The goal is to find the leftmost pivot index if multiple such indices exist. To better understand this problem, let's take a look at an example. Imagine I have the array 1, 7, 3, 6, 5, 6. First, I need to identify the sums of the elements to the left and right of each index. For index 0, there are no elements to the left, so the left sum is 0. The right sum is the total of all elements to the right, which is 7 plus 3 plus 6 plus 5 plus 6, totaling 27. Since 0 doesn't equal 27, index 0 is not the pivot index. Next, I move to index 1. The left sum is the total of the elements before index 1, which is just 1. The right sum is the total of elements after index 1, which is 3 plus 6 plus 5 plus 6, totaling 20. Again, they're not equal, so index 1 is not the pivot index either. I continue this process for each index in the array. When I reach index 3, the left sum is 1 plus 7 plus 3, which equals 11, and the right sum is 5 plus 6, also equaling 11. Since these sums are equal, index 3 is a pivot index, so I return 3. If I were to continue checking the remaining indices, none would satisfy the condition where the left sum equals the right sum. Now, back to the code. The first step in my code is to loop through each element in the array using a for loop, keeping track of my current position with the index variable I. For each position, I calculate the sum of elements to the left and the sum of elements to the right. I start by initializing two variables, current left sum and current right sum, to 0 at the beginning of each iteration. These variables will store the sums of the left and right sides respectively. Next, I use a nested for loop to calculate the sum of elements to the left of the current index I. The inner loop runs from the start of the array up to, but not including, the current index. For each element in this range, I add its value to current left sum. Similarly, I use another nested for loop to calculate the sum of elements to the right of the current index I. This loop starts just after the current index and runs to the end of the array. For each element in this range, I add its value to current right sum. After calculating the left and right sums for the current index, I check if they're equal. If current right sum equals current left sum, I have found my pivot index, so I return the current index I. If I finish looping through the array without finding a pivot index, I return -1 to indicate that no such index exists. Let me provide another example to illustrate how this works. Suppose I have the array 1, 2, 3. When the outer loop starts, I is 0. For this position, current left sum is 0, because there are no elements to the left of the first element. The current right sum is the sum of all elements to the right, which is 2 plus 3, totaling 5. Since 0 doesn't equal 5, I move to the next index. Now, I is 1. The left sum is 1 and the right sum is 3. Again, they're not equal, so I move to the next index. When I is 2, the left sum is 1 plus 2, which is 3, and the right sum is 0, still not equal. Since I have checked all indices and found no pivot index, I return -1. This algorithm has a time complexity of O of n to the power of 2 because I use nested loops to calculate the left and right sums for each index. While this approach works fine for smaller arrays, it may not be efficient for larger ones. There are more efficient ways to solve this problem, but this method is straightforward and easy to understand for beginners. In conclusion, to find the pivot index in an array, I loop through each element, calculate the sums of elements to the left and right, and check if they're equal. If I find such an index, I return it. Otherwise, I return -1. This method provides a clear and simple solution to the problem, though it may not be the most efficient for larger arrays. Now, let's run this algorithm and check if it works. By testing the code with different arrays, we can verify its accuracy and functionality. Remember, you can always experiment with your own ideas and implementations to find solutions that might be more efficient than the one I've presented here.